In 1981, IBM PC-DOS established the baseline for sequential, isolated computer architecture built for a single user on a single machine. The execution model of MS-DOS is strictly passive and synchronous. A program is a single-entry module that lacks native concurrency. It can only process one command at a time and does nothing until explicitly invoked. When you observe this data matrix collapsing into a single processing line, you're looking at the central architectural paradox of modern Web 3. Decentralized networks claim to be globally distributed, yet their execution environments rely entirely on the exact structural DNA of MS-DOS. To achieve scalable, parallel execution on a global ledger, developers must move beyond the shared state DOS model and implement pure object-oriented invariants. Scaling a global decentralized network is mathematically impossible when constrained by an SISD execution environment. SISD stands for Single Instruction, Single Data, a processing architecture where one processor executes one stream of instructions on one set of data. The abstract smart contract data model is a self-contained unit. It combines executable code and persistent state, anchoring both to a single addressable network entity. This split-screen diagram shows how a flat DOS.com file and an Ethereum-style EVM smart contract share the identical architecture. Both models co-locate code and data into a single module with zero internal separation. Neither system possesses autonomous execution capabilities. They sit entirely inert until an external message strikes, triggering a single top-down execution thread. Both systems restrict execution with zero native concurrency. Multiple simultaneous inputs are forced into a strictly sequential processing queue. Interaction with other programs in both environments requires synchronous, blocking communication. The caller halts entirely and waits for the callee to return before proceeding. These systems operate within a globally shared mutable state space. The totality of the environment's memory, or ledger, is treated as a global commons, accessible to all participants. While DOS requires programs to explicitly write state to a disk to persist it, and smart contracts persist state implicitly by default, they utilize the exact same structural logic for state durability. The deployable unit is the atom of identity. Both models provide zero intrinsic access control. Security enforcement is delegated entirely to the application layer, forcing developers to build custom guards for every deployment. Abstract smart contracts are effectively DOS programs, adapted with atomic state transitions for a replicated environment. Attempting to optimize current smart contract networks means optimizing a 40-year-old single-threaded paradigm. This permanently bottlenecks decentralized throughput. When thousands of independent nodes interact within a global shared state model, the execution environment inevitably degrades. This diagram illustrates the mathematical bottleneck created by shared state. When disjointed user accounts attempt to execute against a single, centralized smart contract, the system forces these parallel requests into a single serialized line. Because all callers hit a single co-located address synchronously, the execution stack becomes a blocking LIFO stack. LIFO means last in, first out, where the most recent transaction to enter the stack must process before any prior ones can complete. This causes concurrent transactions to pile up and halt. To prevent total state corruption, the network enforces strict atomic state mutations. Atomic means the state transition is all or nothing. It either fully completes or completely reverts. Traditional network sharding fails under this model. You cannot partition a globally shared state without instantly breaking those atomicity guarantees. The blockchain industry's primary response has been to brute force consensus speeds, attempting to process the single file line faster rather than correcting the underlying execution architecture. Any system centralizing state into passive external contract accounts will inevitably degrade to serialized execution. This effectively neutralizes the benefits of physical network distribution. In 2003, Alan Kay provided a precise clarification of his original vision for object-oriented programming. The professional software industry largely misunderstood his design. Kay's architecture was entirely about messaging, explicitly rejecting classes and inheritance as the primary features. In this biological model, Kay's first invariant becomes visible. Messaging is the only legitimate interaction primitive. Entities communicate exclusively by firing autonomous protein signals at each other, with no direct manipulation of adjacent structures. The second invariant dictates strict local retention and protection of state. Every object owns its state exclusively, prohibiting shared mutable memory. The third invariant is extreme late binding. The receiving object retains total autonomy to determine how it processes an incoming message at runtime. Kay envisioned a distributed computing network where the physical location of an object is rendered completely invisible to the sender of a message. This biological cell model mathematically eliminates the concept of shared mutable state. It provides the exact architectural blueprint required to unlock parallel decentralized execution. PraSaga SagaTech stack takes K's biological architecture and translates it directly into a trustless consensus environment. The specific implementation mapping these invariants to the ledger is called the Extensible Blockchain Object Model, or XBOM. This diagram shows a single user account in the XBOM structure. XBOM eliminates the need for separate smart contract accounts by placing an internal directed graph of encapsulated objects directly inside the user's boundary. The critical divergence from Ethereum happens here. The executable code lives directly inside these user object instances, achieving state isolation. Because the code is internal to the object, all ledger transactions occur directly point-to-point between user accounts. This localized state architecture automatically unlocks parallel execution across the network. Watch the nodes on screen. Account A and Account B engage in a direct, isolated transaction. Simultaneously, Account C and Account D engage in a separate transaction. The C and D transaction processes without waiting on A and B. They operate within independent blockchain shards, processing at the exact same time. Because these account sets are mathematically disjointed, there is zero risk of cross-contamination of state. This local state architecture bypasses the legacy smart contract serialization bottleneck. The XBOM message passing boundary is language agnostic. Interoperability is defined strictly by the communication protocol, not the syntax of the implementation. Assets, currencies, and even cryptographic signature schemes operate strictly as first-class objects within this framework. Saga OS functions as a decentralized operating system, providing the state-aware infrastructure necessary for a globally distributed platform. By permanently moving code and state into the user's boundary, XBOM achieves deterministic parallel execution, solving the Web3 scalability crisis at the architectural root. If developers are no longer deploying custom, isolated smart contracts, the mechanics of building software on the network require a different approach. The shared platform layer is the single-instance global class tree, managed continuously by the class manager infrastructure. This structural diagram illustrates how developers instantiate objects by subclassing from foundation classes already resident and secured on the distributed ledger. This structural reuse eliminates the need for bespoke bytecode deployment, drastically reducing individual coding vulnerabilities. When disjointed objects communicate across physical space, the network must account for the physical limits of topology, specifically the unavoidable latency of cross-shard gossiping. SagaScale serves as the algorithmic layer designed to combat this physical network latency. Notice how this matrix reorganizes itself. SagaScale predicts account co-locality and dynamically shifts account clusters across boundaries. It ensures related objects exist on the same physical shard before executing. SagaScale provides the critical routing intelligence required to make K's location-agnostic execution viable on a physically fragmented blockchain topology. To maintain strict ledger determinism, Saga OS tightly bounds K's theoretical ideal of extreme late binding. Every node must reach the exact same result. Achieving Byzantine fault-tolerant consensus introduces non-trivial coordination costs and economic token constraints. Byzantine fault-tolerant consensus is a network's ability to reach agreement even when individual nodes fail or act maliciously. Pure local state models never had to account for these specific variables. Despite these engineering compromises, Saga OS deploys strict message passing invariants within a trustless adversarial environment. As these vector shapes link into a seamless network lattice, the ultimate vision emerges. The Internet becomes an object-centric, globally distributed computer where the artificial boundary between local and remote computation is erased. A future of decentralized systems relies on enforcing the rigid isolation of true message-passing objects, not optimizing an execution architecture from 1981.